Hi there, so this is our 10 questions on SUVAT and motion graphs. As usual, I'm going to talk through each question and give you an explanation for the correct answer. It's obviously a good idea for you to complete the questions before watching this video, and there is a link to the document in the description for this video. All of these questions are IB past paper questions, a mixture of SL and HL. And so, as I say, I sort of heartily encourage you to try them before watching this video. Okay, on with the show. We're looking firstly at motion in a straight line, so 1D motion. And we're looking at the variation of displacement with time. We are looking for the graph which shows motion with negative acceleration. Let's think a little bit about what negative acceleration means. It means acceleration down, or we are decelerating up. Okay, in other words, we're expecting something which is slowing down. We've got to link that to our displacement time graph, and we do so via the fact that the gradient of a displacement time graph is the velocity. We therefore need to find the graph which shows a decreasing gradient, because that would show a decreasing velocity and therefore a negative acceleration. And that one is our graph D, which obviously is curving down. It's got a decreasing gradient, therefore a decreasing velocity, and therefore a negative acceleration. Okay, so that's why the answer here is D. Okay, let's think about A, B, C, and D. Well, here we've got straight lines, which means constant velocity, and here we've got curving up, which means acceleration, a positive acceleration. Next one, we've got the variation with time of acceleration A. This is an acceleration time graph. Now, you may not have met many of these in your course. However, this is one that you should be able to deal with. Okay, we know that acceleration and time, if we multiply them together, meters per second squared times seconds, that gives us meters per second. In other words, some kind of velocity. And actually, what we're getting here is that the change in velocity is just the area under the graph. We therefore need to calculate the area under our shape. I split it up into three. The first one there, we've got 1 times 2, 2 meters per second. We then got this rectangular shape here, so we're going to go 4, so that's 6 minus 2, times 1, well that's just 4. And then we've got this triangle here. Well, if it was a square, we'd be doing 4 multiplied by 2, okay, because that's our height. However, we have to divide it by 2, so again, we've got another 4. We add those together, we've got 2 plus 4 is equal to 10 meters per second. This is a really nice question, and it's one which requires you to read it carefully and think about your answer. We've got a ball falling from rest, and the position of the center of the ball is determined at 1 second intervals. We want to know the distances traveled by the center during each second for the first 4 seconds. To do this, we need to use our equation, S equal to ut plus half at squared. And remember the fact that u is 0, and so therefore we're left with half at squared. We then do some calculations, and we find the displacement at each interval, 0, 1, 2, 3, and 4. That leaves us with initially the answer which we might go for, which would be C here. However, C is the displacement after each time. In other words, it is the total displacement. What we want to know is the displacement during each second. And so what we need to think about is, how far did the ball travel during the first second? Well, 5 take away 0 is going to give me 5. During the second, after the second second, we have done 20 meters of displacement, and the change is 15, because 20 take away 5 is 15. So that means during that second, we traveled 15 meters and not 20. Similar for 3 and 4, we traveled 25 and 35, and so therefore the answer here is actually B, not C. This one, we've got a stone being thrown downwards from a cliff, from the edge of a cliff, with a speed of 5 meters per second, and it hits the ground 2 seconds later. What is the height of the cliff? In other words, what is the displacement? And again, we're going to use our equation S equal to ut plus half at squared. We know u, which is 5. We know the time, which is 2, and as in the previous question, which I didn't quite go into, we know the acceleration, which is 10. Now, we're going to be a little bit careful here, and I'm going to write this out fully, because I've decided, and this makes most sense to me, to put down as negative. Well, if we're thrown downwards, then that means my initial velocity is minus 5. My gravity, in order to take into account that, also has to be a negative value, and so in this case, it is minus 10. Ignore this typo here. That means we're left with a displacement of 30. In other words, the height is 30. We've got a truck with an initial speed of 20 meters per second, and it decelerates at 4 meters per second squared. What is the distance? Remember, when we're talking about speeds and distances, we can also think about velocities and displacements. Those are the same here, they just have a direction. Initial velocity here is 20, and an acceleration or a deceleration of 4 meters per second squared is an acceleration of minus 4. We then want to know the distance or the displacement. When you think about what else we know, we also know that when we finish this journey, our velocity is 0. So we've got final velocity, which means we want to use our equation v squared equals u squared plus 2as. In this case, v is 0, okay, and u squared and acceleration are quantities that we know from the question. We know the initial velocity is 20, and we know that the acceleration is minus 4, in other words, deceleration of 4, and we can rearrange so that we get 8s is equal to 400. In other words, s, the displacement, is 50. This is a great question, and it's one which really takes a lot of understanding and a lot of thinking about the way that the equations work for SUVAT. We're looking for a relationship for v and s, so what I encourage you to do is to start off by thinking which equations have v and s in them, and then go from there. Now there are two, but the one that we're going to choose is our v squared equals to u squared plus 2as. Why? Because we also, in this question, we know about the runner starting from rest, and we also know about acceleration. So we're looking for initial velocity, which was 0, and that helps me get rid of the u squared, and we've got an acceleration here. There are other equations that we could use, however, this is the one which will get us the answer. Now, we know then that v squared is equal to 2as. Well, if I square root, then I'm left with v is equal to the square root of 2as. And therefore, I've got v is equal to some constant times the square root of s. Now, if we go, our answer therefore is a, because this is the shape of a square root curve. Let's think about the other graphs we've got here. This is a straight line, so this would be v equal to k times s. This would be a square term, and so therefore this is v equal to k times s squared. And this one, the v is constant with s, and so therefore there would just be v is equal to k. All right, this is the only graph which shows the square root behavior that we're looking for. We want to know the acceleration of this ball now. Okay, we're told the time intervals, and we're told that there are 6 pictures, and so therefore 1, 2, 3, 4, 5 time intervals. The total time is therefore 5 times our 1 millisecond. Okay, and we're also told our total displacement. We need to think about what equation to use, and again this time we're going to use our old friend s equal to ut plus a half at squared. Why? Well, because we know u here is 0, we want to know a, we know t, and we know s. So if we want to calculate a from there, all we have to do is sub in our numbers. Now that's our displacement, 0.05. Our time is 5 milliseconds, and if you put that in, that's 5 divided by 1,000, that is 0.005 seconds. We need to convert here to our SI. A bit of rearranging gives us 4,000 meters per second squared. Question 8. This is one you need to read carefully. We've got an object released from a stationary hot air balloon, and then we've also got one which is being released from a hot air balloon which is rising at constant speed. no air resistance, and we're wanting to know what does not increase for the object released from the rising balloon. Now, there's multiple ways that you can think about this. Now, I like to think about it in terms of the two balls you can see on the screen, 1 and 2. Ball number 1 is the one from the first situation, where we have a stationary hot air balloon, which just simply falls down. Ball number 2 is going up and then back down again. And that is the situation from the hot air balloon, which is rising up. Let's think about those two animations that we just saw. Ball number 1 took a much shorter time than ball number 2. Ball number 2 also travelled a greater distance. And so these two answers A and B are out. Then we could think about section C. Well, if you think about it, my ball number 2 rose up to a greater height, which means it's going to spend a longer time accelerating, and therefore it's going to reach the ground with a greater speed. Therefore, the acceleration is the only one left over. Now, another way of thinking about this problem is, what is not increase is another way of thinking about this is, what is constant? What doesn't change basically means what is constant. Now, because we have no air resistance, we have no opposition to the motion, and therefore when the ball is falling, the acceleration is simply g. And therefore we have got a constant acceleration equal to minus 9.81 or minus 10 if we're doing our multiple choices. Last couple of questions. Number 9. A ball is tossed vertically upwards with a speed of 5 meters per second, and we want to know how many seconds will pass before the ball returns to its initial position. Again, I'm going to use s equal to ut plus a half at squared, and I'm going to put in my values. Now here we've got to be careful because we're initially traveling up, so the velocity is 5, but because we've got to think about direction, the acceleration is minus 10, that's my g going down. I've used s equal to ut plus half at squared here because I know that when we returned to the initial position, my displacement is going to be 0. I'm at the original position, and therefore my position has not changed. Why we do that is because we can then set up a quadratic, which is equal to 0, and then we can do some factorizing. We've got 0 is equal to 5 times t multiplied by 1 minus t, and so there are two solutions to this. We've got at 0, well obviously at 0 we are at the initial position because we defined that. However, after 1 second we are also at 0, and so therefore B, the answer there is 1 second. Last one, and then we're done. This is right, we've got to think right back to that first question about the acceleration time graph. Again, we mentioned we want to know the change in speed or change in velocity here. Again, the change in velocity is the area under an acceleration time graph. So all we have to do is multiply that base and that height and then divide it by 2, and we're left with c, which is 36 meters per second. As I say, I really hope you've taken the time to look through those questions, try them yourselves before listening to the explanation. If you've got any questions, please do let me know. And I hope that helps you understand a little bit more about how we use SUVAT and our motion graphs. Thanks for watching.